Well, I guess I lied. I'm actually going to do example problem 10. Well, here we go. So suppose E and F are two events, and the number of occurrences of E and F is 420, and the number of occurrences of E is 740. What is the probability of F given that E has occurred? So the way this works is as follows. This vertical bar is read given that. So the probability of F given the E has occurred is, and since we have this count of notation, I'll use that. You can call this the number of times E and F occurs, divide by the number of times E occurs. So we have 420, 740, and now we're going to write these fractions in simplest form. And I'm going to start with 420. I know that that's 42 times 10, and I know 740 is 74 times 10. So I got a good start on my factoring, because those are a factor of 1. 10 divided by 10 is 1. So I've got 42 divided by 74, and I know that 42 is 6 times 7. And 74, let's see here, I believe that's 39. But let's just check. 3 times 2 makes 6. 37. Good thing I checked. Let's see. 2 times 37. And the only thing I can eliminate here is a factor of 2 over 2. And be careful how you write that. 21 over 37. And if you need a decimal approximation, you can use a calculator to get one. And then remember that it's also handy to consider the general multiplication rule. So since the probability of F given E is the probability of E and F divided by the probability of E, that means that if you multiply both sides by the probability of E, you get probability of E times the probability of F given E is the probability of E and F. So think about it sort of like if 2 equals your favorite number divided by 3, that means 2 times 3 equals your favorite number, 6. So let's do another one, shall we? Oh yes, as advertised, I'm going to go back to this definition box on page 292 and walk through that with you. Definition, page 292. Two events E and F are independent if the probability of E given F equals the probability of E, or equivalently, if the probability of F given E is the probability of F. Let's just break that down for a moment. We have probability of E given F equals, by definition, probability of E and F by the probability of E probability of E. But then the book says that the only way, if probability of E given F has to equal the probability of E for this to be true, and if probability of F given E equals, by definition, the probability of F and E over the probability of F. So now we know that, now so then why would that even be true? Let's think about that for a moment. This is just how we've defined conditional probability, and why does independence give us something like this? Why would the probability of E given F be equal to just the probability? I think I've written these backwards. I'm sorry, let me go back for a moment. I think I wrote these backwards. silly me. I feel so silly. You can go ahead and skip the video ahead for a couple moments. I'm pretty sure I wrote these down backwards. So we know from our previous slide that the probability of F given E, yeah, see, I wrote these down backwards. So the probability of E given F is the probability of E and F divided by the probability of F. That's conditional probability. Now remember, if events are independent, we have that the probability of E and F is the probability of E times the probability of F divided by the probability of F. And those cancel. See, aren't you glad that we warmed up on those fractions? That's the probability of E. So that's why that works. And the probability of F given E is, of course, the probability of F and E over the probability of E, which, if the events are independent, then this numerator we can write as a product over probability of E, and we get probability of F. So that's why that works. Now let's solve a problem. The probability that a randomly selected individual in the U.S. 25 years and older has at least a bachelor's degree is that. The probability that an individual 25 years and older has a bachelor's degree, given that the individual lives in Washington, D.C., is that. Are these independent? So let's write down the probability of degree given Washington, D.C. These are not the best letters, but whatever, I guess they'll work. That's 0.485. And the probability that you have a degree, and are let's see, what's the other event here? 25 equals 0.279. So, are these events bachelor's degree? You know what? I wrote these events down wrong. I'm sorry. Let me back up again. Thank you for your patience, which borders on the eternal. Okay. So we have, let's say this. Let B be the event bachelor's degree. And we'll let W be the event Washington, D.C. lives in. So the probability that you have a bachelor's degree, see, the 25 years and older, that's just a red herring. We don't need that. Probability of B is 0.279. The probability of B given W is 0.485. So remember, going back to our definition, if these events are independent, the probability of B given W should be the probability that someone lives in Washington. It's not looking too good for this. And so that's why the answer says no, the events are not independent, because the probability of a bachelor's degree, given that you live in Washington, D.C., is not the same as the probability of living in Washington, D.C. So there again, back on page 292, that's where you can use that definition of independence to answer interesting questions like this. And I'm going to stop the video here, and we'll come back and finish up these last 4 problems in a final video.